In the third section of Unit F, we're going to deal with similar triangles. We're going to start out with congruent shapes and then move on to the similar shapes, which really we're going to focus on similar triangles. So congruent shapes are shapes that are exactly the same, and they have less use in math, but they are just in here to be compared to the similar shapes. So congruent shapes are exactly the same. You can think of them as copies of each other. Their angles are the same, their lengths are the same. They might be oriented differently, but these are exactly the same shape. So these two rectangles would be congruent. Similar shapes, on the other hand, might be slightly different. So they'll be scaled up or scaled down versions of the same shape. So they have the same proportions. Similar shapes have the same proportions, even though one might be bigger and one might be smaller. The shapes that are similar have sides that are different lengths, but all the angles are the same. So that's one of the ways, and this is the first example of a similar triangle. This one is really a smaller and a larger version of the same thing. So this is a scaled up version. So we're going to use this to investigate this concept of similar shapes. And then on the next page, there's actually three proofs. There's three ways that we can look at triangles to say, yeah, those would be similar triangles. So the first one here is scaled up, and like it says, the angles are all the same. So we have a 40, a 90, and a 50-degree angle. So all of these angles are the same, and by definition, the sides will have the same relationship to each other. So this scaled up version, if I take the longest side of the small triangle and put that over the longest side of the larger triangle, and I take the smallest side of the small triangle and put that over the smallest side of the large triangle, and then the medium side over the medium side, what I can find is that these sides are proportionate to each other. In the last unit, in rates, we tested to see if things were proportionate by doing a cross product of them, if you remember that, right? You could do the cross product in any two of these three, and you're always going to find the same. You could also think of them as similar fractions. We could reduce all of them down to a 1/2, right? And so this is two different ways of showing that these sides are proportionate to each other. And that would make these triangles similar triangles. So we're looking for relationships between angles and sides. And the next page, we're going to say there's three different kind of scenarios we could look for to say that two triangles are similar. So on the next page, the first example is sort of what we just looked at. If the angles are all the same, then they're going to be similar triangles. So we have a 25-degree and a 25-degree and a 65 and a 65. Now, this could be actually angle, 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 because if two of them are the same, then the third one is going to be 180 minus those first two. So I think when I ever learned this, it was angle, 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 but technically that's a little redundant. You don't really need to. We could always calculate the third angle, and in this case, if we take 180 minus the 65 and minus the 25, that's going to tell me 90 degrees. That actually shows that this is a right triangle, which can be a useful piece of information to sometimes come up with. But regardless, these are similar triangles. They're just scaled up or scaled down versions of each other because they share the same angles. The next scenario deals with the sides. And so in that first example, we did this calculation to see if the sides were proportional. And you can always do that. Check all the sides. It can be tricky depending on the orientation of the triangles. So I tend to go with the longest side on both triangles, and maybe the shortest side on both triangles, or the shortest side that's labeled, right? If we have two of these that are proportional and they're enclosing an equal angle here, so whatever that is, I don't know, but it has that one bar across it, so that would show that it was the same. Kind of like we had the two lines on the isosceles triangles, or the three lines on the equilateral triangles. You can do the same thing for angles. So this proof is a side, angle, side. You can see down here that it went through and figured out that they were both proportionate. You could also do the cross product like we had done in the rates unit to show that these are proportional. Whoops, not 18. Sorry, I got ahead of myself. Yeah, let's go 27 on that one. Okay, so that's the second reality that shows that these could be similar triangles, a scaled up and a scaled down version of each other. The third one is if all the sides, all three sides, so side, 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 are proportionate. So the last example had just two sides in an angle. This one, if all three are proportional to each other, then that's going to prove that these are the same, you know, sort of triangle. They're just scaled up versions of each other. And so these are sorted again, you know, you could put the bigger over the smaller, as long as, this is a key thing to notice, especially when you're doing this one, if this is my triangle here, those are the numbers on top, and they're all on the top. You have to be consistent with this, or you will find that things don't work out. Same thing, the numbers on the bottom all correspond to this triangle. So be consistent with that, or you might find that you don't think that they are proportional when they actually are. So let's practice applying these. The following page has triangles that may or may not be proportional to each other. And we're supposed to look at what the proof would be that these are proportional. So off the top here, we have some angle markings and we have all three sides. So from the angle markings, it doesn't look like they're similar. But we have more information, so let's test that out. Let's do the proportionality of the sides to double check. So I'm going to take the longest side on this one and put it over the longest side on that one. And that should equal, I'll go the shortest side on both, so 10 over 25. And then the medium side, so 12 over 30. If I were to reduce all of these, and quite honestly, I threw them in my calculator, you know, I get a 2.3 repeating on this one, I get a 2.5 on this one, and I got a 2.5 on that one. It's a lot easier to do that and figure out if they're all the same value, because then you could, you know, prove that they are similar or congruent. Sorry, wrong word. Similar. Congruent would be exactly the same, and they're not. So the sides are not proportional, and so this one actually fails. These are not similar triangles. All right, let's move on to the next one. Hopefully this one gives us a little more luck and I don't say the wrong word. So this one we've got an angle that's the same, and we've got two sides on each triangle. This is setting it up that it could be a side angle side. But let's take a look at those sides and see if they are proportional to each other. So I'm going to go with the bigger over the other bigger, right? So the 8 on this one over the 1 point, oh, that's not the one, big one. The 2, sorry about that. It does get confusing when they get spun all over the page. And then I'll go 6 over the 1.5. So again, the 6 and the 8 are from this triangle here, and the 2 and the 1.5 are from the other. So if I did these, I could, in my calculator, figure out that they both work out to 4. Or I could do the cross product, which is something that we've already done in another unit, so you can leverage that to show that they are proportional. So that would mean that these are two similar triangles, and the proof of that is side, angle, side. They share that 90 degrees, and the two other sides are proportionate to each other, or proportional to each other. So the next one down the page, we have all three sides labeled for us. We can see that this would be an isosceles triangle. Other things that we'd know that whatever this angle is would be the same as this, right? But let's just double check. We don't have actual information about those angles, so let's just look at the sides. What we could hope to find is a side, side, side proof of similar triangles. So let's put the longer over the other longer, right? The longer on this one over the longest on that one. And then the others are the same. So I could go 20 over 5. I could write that out again, but it's going to have the same value, obviously. So there's two ways to do this. You can figure out what that equals on your calculator, or you can do the cross product of them. And either way, you'd find that they are proportional to each other. So these are similar triangles, and the proof of that would be side, side, side. Even though I didn't calculate that last side, it's the same value, and so I didn't really need to. Moving on to the next one, I have some angle markings on this one. I have no sides on this one. So I guess I have to take the word or assume that the person that put these markings on here put them on to show that those two are equal and these two are equal. You know, with deduction, you could figure out that this one would actually equal this one, but we don't need to go that far. So these would be similar triangles, and the proof would be angle, angle, or angle, 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 if you want. The last two down here, you can take a look to set them up. They are going to be similar triangles. I've done my answer key for these, and the proof of these is going to be side, side, side. So take a minute to set up your ratios so that you can prove to yourself that they are similar triangles. So we can take this a little bit further here. These ones are a little bit more challenging. We want to know, are they similar triangles? And if they are, how do you know that they are? So the labels on here are a little wacky. Sorry for that. We've got two different triangles, and we've got some angles on them. So we've got a 21, 105, 54, and 21. I can always do the investigation to figure out this missing angle. I could take 180 minus the 21 and minus the 105, and when I do, that works out to 54 degrees. So that's looking promising because I have a 54-degree angle on the other triangle. You don't need to do this, but just to be sure, we can calculate the missing angle in the second triangle as well. Subtracting what we know from 180, we find that it matches. It's 105 degrees. And so this angle in here is 105 degrees. And so they weren't labeled. The given information didn't tell you that they had two angles that were the same, but with a little bit of extra sleuthing here, we could say that these are two similar triangles, and the proof would be an angle-angle reality here. So we're back to the parallel lines. So we could always say that, X and Y are parallel to each other with those little markers. It tells me that in the question. And I put this one in here because this is often a way that triangles are labeled, and are they similar? So they're not actually equal to each other, but they are related to each other. They're scaled up and scaled down versions. So to figure out this one, we're going to have to remember some of our angle proofs. And so we know that we have opposite angles. So this angle here and this angle here would be the same. We know that this angle and this angle would be the same because of the Z pattern. We also know that if we subtract these two angles from 180, whatever this is going to be the same as that. And that also could be shown with the Z pattern. So by a little bit of deducing, we would say that yes, these are similar triangles, and the proof of this would be an angle-angle reality. So a little bit of applied knowledge from the earlier sections, but we can now relate this to this concept of similar triangles. So we're told the triangles below are similar, and if we are told that they're similar, this is the first time that we're going to be able to do something with that. So we have an angle and an angle, those are the same. We have an 18 between that angle and the right angle, and we have a 12 between that angle and the right angle. So what we've got going on here should be similar triangles. If they are similar, this 16 should be proportional to whatever this EF segment is, or this EF side is. So rather than proving it, what we can do is set up with an unknown to figure out what that unknown is. And so I could go 16 on my little triangle over the 18 on my bigger triangle should equal the 12 on my little triangle over, I'm going to call it X, just because it makes the math a little bit, or the algebra a little bit easier, right? So we remember that we did this before. You could have top times the bottom equaling bottom times the top. And then you divide by 16. You probably got good at this in the rates unit. Hopefully you did, because you can do this in one fell swoop. You know, this is me showing my work if you're still a bit rusty on it, but I honestly start with this and just put that in my calculator. I would do 18 times 12, the two that you can multiply, but divided by the number that's going to end up with the X. So either which way, showing your work or not, I'd get down to X equaling a 24. And that is because these are proportional, right? They are similar triangles, and we can leverage that knowledge to know that this side should be related to this side. So the last two in this section are problem solving. They're word problems. Most of these ones come with pictures, which makes it a lot easier. Just gonna scroll in a little bit. So in this one, oftentimes there's shadows or that sort of a thing, because if there's a sun, it's always going to project rays of light at the same angle, right? And so if there is a shadow down here, we can set up proportional triangles because of that angle and the enclosed angles. So here we have a tree forming its shadow, and it would be similar to the triangle formed by the person and her shadow. We want to try and figure out what is the height of the tree. And so we could start with the height of the tree is going to be proportionate to the height of the woman, and the length of the shadow of the tree is going to be proportionate to the length of the shadow of the woman. And so if you're diligent in sorting, you can write this any number of ways, so long as you sort so that you have, the similar things together, you should end up in the same place. And so I'm always on my key a little light on showing my work on this, and I honestly do all this in my calculator. I would have 1.6 times 36 divided by 2.4. I'm going to show it one more time with all the work. So top times the bottom, and write that on one side. Bottom times the top times that 36, and you divide both by 2.4. So if you don't need to show this work, you don't have to, but that's how you'd get what H equals. And however you get there, the height of the tree would equal 24 meters. All right, you may see this pyramid Khufu come up again. This is a question about Indiana Jones. I don't even know where this one came from. So Indiana Jones is trying to measure the height of a pyramid. So we've got the height of a pyramid. I'm going to skip drawing. And the only thing that he has is a meter stick and the sunshine and his brain. So he measures the length of the pyramid shadow and finds that it is 6.94 meters long. So this is the height of the pyramid, and this is the length of the shadow. Next, standing the meter stick on its end, so we'd have a 1 meter tall meter stick, he'd find that the shadow is 0.05 meters long, drawn way out of scale. I don't even have to draw the third side of this triangle. The key thing here is that the angles are all going to be the same, right? Because of the angle of the sun. So setting this up as a proportionality statement, because they are similar, the height of the pyramid over the height of the ruler would equal the length of the shadow over the other shadow that is made. And so setting this up using your calculator, 1 times the 6.94 divided by 0.05, or take your time to show the work. Regardless, you'd end up with the same spot of 138.8 meters for Pyramid Khufu.